I'm in the mood to talk about the infinite imaginary tower more. Because I think a lot of students, they see something like the square root of 2 and they think, okay, it's pretty weird, right? Because it's got the infinitely many digits if you're in base 10. It's a little bit weird, but then, you can draw a triangle, length 1 there and length 1 there, and, root 2 for the hypothesis. It's like, okay, root 2 isn't that weird, right? Same with pi. It's the area of the unit circle. It's not too weird. You can picture it in a pretty straightforward manner, at least. And then you get to I, right? And I is the square root of -1, so to speak. I don't know why I'm saying so to speak. And a lot of people are quite skeptical of I. It's a little bit too weird for most people, but people sometimes do kind of get, somewhat used to it. They're like, okay, I'm suspicious, but fine, right? Fine. And then you look at I to the power of I. Now people are saying, okay, what are you talking about? What are you talking about? This is starting to feel a little bit too weird. And then you talk about I to the power I going on forever. And at that point, it's like, are we even doing math anymore? Is this math? Now, philosophically speaking, I do have a position on this. And here's my position. If you accept the existence of the real numbers, then to accept the existence of the complex numbers is a very tiny leap to make. It's basically a trivial leap. So, right, if we're leaping from assuming this exists to saying that this exists, that's a very tiny leap. Because in fact, the complex numbers can be constructed from the real numbers as just ordered pairs of real numbers. So if I take an ordered pair of real numbers x comma y, for instance, I could think of this as the complex number x plus iy. Now, I do have to define complex arithmetic on these ordered pairs. So the way it works is you have x comma y. Actually, let's use a's and stuff. So I don't know why this comes off so easily. So a comma b plus c comma d is going to be defined to be a plus c comma b plus d. So that's kind of like saying if I have a plus I times b, and then I add that to c plus I times d, where I have sort of parentheses around these, then that is going to be equal to just, a plus, that's just going to be equal to a plus c plus I times c plus, oh my gosh, d plus b. Sorry about that. B plus d, that's supposed to be b plus d, but it's the same thing. So I just defined complex addition. And then I can define complex multiplication as well. Okay, I guess that's just not going to stay on. So a comma b, complex multiplication times c comma d. Okay, no more messing up here. It's going to be ac minus bd, comma ad plus bc. So that one looks a little bit weird, right? But that all I'm doing is just taking a plus ib. If you want to see where it comes from, where the idea comes from, I'm just FOIL multiplying these together with the rule that I times I is -1. So a times c, that's a times c, and then ib times id, well, b times d is bd, and I times I is -1, so that's where the negative comes from. And then those are both going to be the real number parts, or this is the real number part. And then a times id is going to give me the AD over here, and B times C is going to give me the BC over here, and this latter part is I think of it as all being multiplied by I. But in fact, I've just constructed the complex numbers as ordered pairs of real numbers, with complex addition being defined, with complex multiplication being defined. And that means that I itself can just be thought of as 0, 1. Okay, so i's not that weird, but what about I to the power of I? Because that seems a lot weirder. And here the problem is you have to define what complex exponentiation is. So you start with e to the power of a complex number, and you define that to be 1 plus z plus z squared over 2 factorial plus z cubed over 3 factorial, and it goes on forever like that. And in fact, no matter what complex number you pick, this will converge, which means if I start with 1, and then I look at 1 plus z, and then I look at 1 plus z squared over 2 factorial, and if I keep adding more terms, that I will be getting closer and closer to some complex number. By the way, what is the distance between two complex numbers? It's just going to be... Actually, you know what? You can just define the norm of a complex number, so that's just going to be the magnitude of the complex number. And that is just going to be defined to be the square root of a squared plus b squared. So that's how far away the complex number is from the origin, if you're to like sort of draw a line to it. So with this norm being defined, you can use the norm to get a notion of distance, which you can then use to talk about convergence, and this is going to converge for anything. So we've just defined complex exponentiation. And by the way, if you know what derivatives are, the derivative of the 1 vanishes, the derivative of z is 1, the derivative of z squared over 2 factorial is z, the derivative of z cubed over 3 factorial is z squared over 2 factorial, and so on. So when you take the derivative of all the terms, you know, simultaneously, so to speak, you just get the same thing back exactly. Okay? And then if you want to define a complex number to the power of a complex number instead of just e to the power of a complex number, you got to talk about the log or the complex logarithm. Okay, now this is many to 1. There will be, you know, it maps different points into the same point sometimes. In fact, for any point, I can find infinitely many points other than 0, I guess. I'll be able to find infinitely many points that get mapped into it. So it's many to 1, and this is 1 to many. So this is not a function, it's multi-valued. Sorry, I'm explaining this very quickly, because I'm not that hung up on the details right now. But basically what we can do is we can define z to the w to be, by definition, e to the w log z. So we're basically just doing a base change. So I to the power of I is just going to be equal to, by definition, e to the power of I log I, which is multi-valued. But we could pick out a particular value for it if we want, so I could write that as e to the capital L log I, so I'm taking the principal logarithm. Now this is just a single value, and I times capital log I is in fact just going to be equal to, oh, I don't know, probably like negative pi over 2, right? Unless I'm dropping the ball right now. So now I really just have e to the power of negative pi over 2. Well, what's that? Well, e to the power of negative pi over 2 is just going to be equal to that series, right, that I had with negative pi over 2 playing the role of z. Well, what is negative pi over 2? Well, I'm thinking of negative pi over 2 right now as a complex number. So it's really the ordered pair of real numbers, negative pi over 2, and I guess it doesn't have an imaginary part really, so the imaginary part is just 0. So basically this infinite series would be 1 plus or I guess 1 would be written, if I wrote it as an ordered pair of real numbers, it would be this plus this plus this thing squared over 2 factorial, which 2 factorial, I'm not going to bother writing that, you know, in its complex number notation, plus this, and then going on infinitely like that. By the way, this thing is itself times itself, and complex multiplication was defined earlier by that formula, so I can actually work out what this thing is. And then I can divide it by 2 factorial. I didn't talk about division, but it's pretty obvious how that's going to work, basically. And then I can add the 2, because I defined complex addition. So here, hiding in here is complex multiplication. Hiding in this division by 2 factorial is another complex multiplication, except we're complex multiplying by the inverse of 2 factorial. And then I'm going to be complex adding these 2. And this is an infinite, this is a series, so there's going to be a notion of convergence. And because the complex exponentiation always converges for any input, the series converges for any input, it in fact does have some particular value. I don't know what that value is off the top of my head, but it's going to be something in this case between 0 and 1. Yeah, something like that. Something between 0 and 1. Closer to 0 than to 1. So then what about I to the power I infinitely many times? Well, that's just the limit of I to the I, and then I to the I, and then I to the I to the I, and then it just, you know, you're just taking the limit of this. And if you can calculate I to the I, then of course you can do I to the I to the I, because I to the I to the I is just I to the power of whatever I to the I was. And you can just keep repeating that. Then you take whatever that thing is, and you take that as a power of I. And then you take whatever that thing is, and you take that as a power of I. And then you see, as you do this infinitely, or as you do this more and more and more, what are you converging to? And there is something that you will be converging to. And by the way, showing that something converges does require mathematical argument. It is a little bit more abstract, but it does boil down to boring old arithmetic with, you know, simple numbers, you know, of some sort. So convergence, it's got a little bit of magic in it. In fact, you know, if you were to try to like answer questions about convergence in the general case, that's impossible. Sorry, ignore. I'm not going to talk about that right now, because that's gonna. I'm almost getting sidetracked right now. It's starting to want to talk about that, and as you can tell, this whole video is me being sidetracked. But anyway, so you can see the infinite power, imaginary power tower. What I'm trying to convey here is that if you accept the real numbers, then it's really not that weird. But what about those real numbers? Because the real numbers are weird. And I think really the jump from rational numbers to real numbers is the really weird, crazy leap to make. Not from reals to complex numbers, that's trivial. But from rationals to reals? Oh, so weird. So what is a real number? We'll call it R. Well, one way to think about a real number is that it is a equivalent class. It is a... Okay, so let's start with the rational numbers Q, right? We can consider what is called a Cauchy convergent sequence of rational numbers. Which means that the pairs of numbers, as you travel out further and further, they're getting closer and closer together toward, you know, converging towards 0, essentially. I don't really want to talk about Cauchy convergence and all that very much right now, but basically, I'll just jump to the end. So a real number, like say the square root of 2, the way it would be constructed as a real number, it would be a set of Cauchy convergent sequences of rational numbers. So in fact, there would be quite a lot of them. So, you know, there would be a sequence there, and then there would be a different sequence here, and there would be a different sequence here. And in fact, there would be too many of these to even list them out. But what they all would share in common is that if I subtract any two of them, the resulting sequence would Cauchy converge to or would just converge, I guess you could say at that point, to 0. And that all of them are getting closer and closer to, we're thinking of it as the square root of 2. And it would be the set of all of these. So it's an infinite set of infinite sequences. Or to put it another way, it's an uncountably infinite set of sequences of rational numbers, particular sequences of rational numbers that are part of an equivalence class. They're all interchangeable with each other as far as the construction of the real numbers is concerned. And all of this can be made definite. So what is a rational number? Well, we could think of a rational number like 3/4 as an ordered pair of integers. Or I guess maybe -3/4 would be the ordered pair of integers like that. But we would have to, again, define rational addition and rational multiplication and rational division and rational subtraction on these ordered pairs. And we would also want to define what it means for one rational number to be less than another, i.e. what it means for one ordered pair of integers to be less than another ordered pair, except I'm actually lying right now, because they're not defined as ordered pairs of integers, they're defined as equivalence classes of ordered pairs of integers. So for example, -3/4, -3, 4 would be considered equivalent to -6, 8. Basically, intuitively, we're thinking of this as being divided by this, and these two are going to be equivalent to each other. Of course, we have to define that equivalence. Once we have done so, they are, for all practical intents and purposes, interchangeable with each other. Okay, well, what is integer? Well, an integer such as -3 would be defined as an equivalence class of ordered pairs of natural numbers, where I am going to consider 0 to be a natural number. So in fact, I can write this one out quite easily. It's going to look something like this going on forever. So I think of this as 0, -3, 1, -4, 2, -5, and these are all equivalent with each other. We have to define that equivalence, of course, but it can be done. And then what's a natural number? Well, we could start with 0. 0 is just going to be defined as the empty set. And then once I have a natural number defined, then the next natural number is going to be defined as all of the natural numbers up to that natural number. It would just be that set. So then x++ would be this set. And so on. And then you can define what natural number addition is. So this is sort of like defining what it means to add 1 to a natural number. And then you can define natural number addition. And you can define natural number multiplication. So it all goes back down to 0 in the natural numbers. And then you can build up to the integers through equivalence classes of ordered pairs of natural numbers. And then you can build up to the rational numbers through equivalence classes of ordered pairs of integers, and then you can go from the rational numbers to the real numbers by equivalence classes of Cauchy convergent sequences of rational numbers, and then you can go from the real numbers to the complex numbers, and actually that one's the simplest conceptually. Those are just ordered pairs of real numbers, and at each step of the way you're defining what the less than means, you know, what the addition, subtraction, multiplication, division, whichever one of those applies, what those mean at that level. And of course with the complex numbers, that's the first place you hit where there is no less than anymore. And then once you've defined the complex numbers, you can go ahead and define complex exponentiation, and then you can define complex number to the power of a complex number through the base change via logarithm, which is going to be multi-valued. And then you can do your infinite power tower, such as I to the power I to the power I ... And if you throw enough mathematical logic at it, enough proof writing, enough abstract maths, you can prove properties of these things. You can prove that the infinite imaginary tower exists. You can provide a way to, approximate its digits if you want to, and you can even discover the z to the power z to the power z going on forever associated fractal, similar to the Mandelbrot set. So, have I demystified I to the I, so on? I think I just made it more crazy. It's like the more you demystify it, the more you crazyify it. You know what I mean? And I find that more exciting. And so yeah, if you have any questions about any of this, please let me know, and I will try to answer it. And yeah, thanks for watching, and take care.